Welcome! In this video, we're going to explore a core element of science, reasoning. Science isn't just about experiments, it's about how we think. In this session, we will explore the three types of reasoning: induction, deduction, and abduction, how they shape drawing conclusions about theories, proofs, and guesses. Then, we discuss Karl Popper, who argued science advances by falsification, and Imre Lakatos, who showed how research programs evolve. And we will see how debates, from Feyerabend's critiques to Feynman's blunt dismissal, keep science alive as a process of questioning, not dogma. In the end, science emerges as a method that thrives on doubt, discussion, and the search for justifiable knowledge. Before we dive into reasoning, let's quickly recap the three phases of the scientific inquiry described by Charles Peirce. It all starts with abduction, a creative leap where we form a positive explanation based on what we observe. Next comes deduction. We use logic to figure out what should happen if our explanation is true. And finally, we reach induction, where we test those predictions through observational experiment and see if the explanation holds up. This cycle, abduction, deduction, and induction, is at the heart of how science moves from questions to knowledge. Inductivism is one of the earliest models of scientific reasoning. It starts with observation. We observe that swan number 1 is white, then swan number 2, also white, swan number 3, still white. From repeated observation like this, we form a general theory: all swans are white. And as we keep observing more white swans, the theory seems to grow stronger. This is reasoning by induction. We move from specific cases to a general statement. The idea is that the more we observe, the more confident we become. However, no matter how many white swans we see, it only takes one black swan to prove the theory wrong. So that's the key weakness of inductivism. General theories based on experience are never fully certain. They are probably true, not absolutely true. There's never a proof. Nevertheless, this approach laid the foundation for how we build scientific knowledge, from observation to generalization. Now, let's look at the three main forms of reasoning in science: induction, deduction, and abduction. We will use a simple example to walk through each. Imagine a bag of beans on a table. The rule here is all beans in the bag are white. We have a situation or case saying that the beans on the table are from this bag, and as a result, the sample beans on the table are white too. The reasoning method of induction starts from specific observations. You notice that all sample beans are white, and you know they are coming from this bag. So you generalize, all beans in the bag must be white. This is common in science, but there's a risk. As we have seen before, one black swan, one counterexample is enough to invalidate our conclusion. Even if the premises are true, the conclusion might still be false. Maybe there are black beans deeper in the bag. Induction gives us probable conclusions, but not proof. This is different with deduction. Here you start with a generic rule: all beans in the bag are white. If you know our sample came from the bag, you can conclude the sample beans must be white too. Deduction is logically necessary. If the premises are true, the conclusion must be true. That's why it's used to prove things. Finally, there's abduction, also known as inference to the best explanation. Here you observe that the sample beans are white, and you know that all beans in the bag are white. So you guess maybe these beans came from that bag. This is not certain, but it is a plausible explanation. Abduction helps us to form hypotheses based on what we observe. To sum it up, induction generalizes from patterns, like training machine learning models from data. Deduction starts with rules and guarantees truth, like verifying algorithms. Abduction helps us guess the best explanation, for example, critical for forming hypotheses. Each has its place, and together they shape how we reason in science and technology. Let's now turn to Karl Popper, one of the most influential philosophers of science in the 20th century. Born in Vienna in 1902, Popper became a professor at the London School of Economics, where he challenged the long-standing ideas of how science works. In the 1930s, Popper introduced a key idea: falsifiability. He argued that what makes a claim scientific is not that it can be proven true, but that it can be proven false, if it were false. This is called the criterion of falsifiability. A theory is scientific only if it can, in principle, be tested and potentially refuted by observation or experiment. That doesn't mean the theory is wrong, just that it's open to being tested and challenged. So for Popper, real science is never about proving something absolutely, but about trying to disprove it and seeing if it still holds up. His model is: start with a hypothesis, not derived from observation, it can come from anywhere, even a guess. Use deduction to derive testable predictions. Then test those predictions with experiments or observations. If the prediction fails, the theory is falsified. This is sometimes called the hypothetical deductive method. Imre Lakatos, a Hungarian philosopher, builds or challenges the ideas of Popper. He argued that science doesn't just throw away a theory completely the moment a test fails. Instead, theories are part of research programs, structured sets of ideas. At the center of a research program is the hard core, the fundamental assumptions. When a theory runs into trouble, scientists usually adjust the surrounding ideas, not the core itself. He offers a compromise. He's more relaxed than Popper. Not all gets falsified, some parts remain. He said we can compare research programs by asking how well they develop, how many new predictions they make, and how progressive they are. In his words, it's not that we propose a theory and nature may shout no. Rather, we propose a maze of theories and nature may shout inconsistent. So for Lakatos, science moves through competing programs, not instant refutations or blind shifts, but through rational, long-term evaluation. Finally, let's highlight that science lives on controversial discussions, critique, and competing perspectives. Paul Feyerabend was afraid of single scientific voices, reducing complexity and yielding propaganda. Science should recognize that different philosophical perspectives can have merit, and that no single viewpoint holds all answers. Richard Feynman dismissed philosophy of science being useless in its entirety. He says, philosophy about science would be as useless as ornithology to birds. Thus, a practical answer to what is science is to see it as a systematic, transparent process aimed at producing justifiable knowledge claims, one that values rigor, openness, and continual questioning over dogma. To wrap up, philosophy of science identifies three key ways we reason: deductive, inductive, and abductive. In practice, science rarely claims absolute proof. Instead, it's an ever-evolving process. At its core, science thrives on critical discussion and healthy skepticism, driving us to refine and expand our understanding continuously.